Hi, I'm Bill Hogue, Vice President of Sales and Marketing with Ohio Semitronics, and today I'm sitting with our President and CEO, John Redmeyer, and on today's segment of Ask the Experts, I'd like to ask John to talk about Hall effect sensors, the different types, both open loop and closed loop, because we find that in the marketplace today there's a lot of confusion about both styles and when should we use which style. And we also want to talk about some of the advantages and disadvantages of the two different types of Hall effect transducers.
I'd like to start with what is the Hall element, or what is the Hall effect. And the Hall effect was actually discovered by Mr. Hall, believe it or not, in 1879. And what he found was that a current flowing through a conductor in the presence of a magnetic field would develop a voltage across that conductor, which is proportional to the current flowing in the magnetic field. So that, in a nutshell, is the Hall effect. Bill, we brought examples of both the closed loop and open loop today. The closed loop is shown here on the left, and what distinguishes it from the open loop is the fact that there's a coil around the core, and that coil has a current that flows in it that exactly compensates or nullifies the current being measured, and when they're in the exact proportion, then that's when there's zero flux in the core. And as you can see, there's some electronics that are required to go with this unit to drive that coil. On the right, you can see a simpler design. This is the open loop. Again, it's distinguished by the fact that there's no coil around this core. The Hall sensor is down inside the gap of the core, down in this area. And there is a small amount of electronics to signal condition the output. I think this one happens to be a 4 to 20 milliamp output. Up above is just an example of one of the most simple forms of the open loop sensor, where you have the Hall sensor on the end of this flex strip and a gap in the core, and that's the complete sensor right there. We've also brought examples of Hall probes. This is an OSI Hall probe right here, much like the drawing that we showed earlier when we were explaining the Hall effect. These are a couple of commercial Hall probes. This is surface mount Hall probe. This is a through-hole Hall probe. All of these can be used in either the open loop or the closed loop configurations.
John, why should a customer use a Hall effect transducer, whether it's open loop or closed loop, as opposed to some other methodology for current measurement?
Great question. I think the answer lies in the fact that the Hall effect can do DC measurement as well as AC measurement. So many of the techniques will only do AC and not do the DC, but the Hall effect will do both. So anytime you need both AC and DC, Hall effect is a good choice. And as we mentioned earlier, the non-contact, the safety that you gain from not having to make a direct contact to the power distribution system that you're measuring on, that resulting in not having a shock hazard. Also, the Hall effect is all low voltage operation, so well below the 24 volt safety level that we normally think of. So non-contact, simple to install, measures DC, and complete isolation are all good reasons to use Hall generators. Now, with respect to why open loop or closed loop, I really think the open loop is a cost consideration. Open loop has some drawbacks of linearity, temperature dependency of the output, zero offset stability, but all that being said, it still is a very accurate method for measuring current at a very low cost. Whereas the feedback style, you actually have to put current windings or windings on the sensor to create an opposing current to the current that you're trying to measure. It requires some electronics to drive it, and there's a cost associated with that more sophisticated electronics. On the positive side, you get greater linearity, you have better temperature stability of your output, and in some cases, because of the transformer action, even better higher frequency response. So you gain those advantages at the expense of it being a somewhat more expensive transducer. Bill, we've been talking about how these sensors work and the difference in the open loop and closed loop. But I know in actual applications, you run across different needs and requirements. You might tell us some of those.
Sure, John. Well, I know some of the more recent applications or I'll say customer solutions that we've been involved in coincidentally have been in the solar industry. The most recent one that we worked on for a customer involved the use of a Hall effect transducer, not for part of the power inversion process, but what they were actually trying to do was use it as a tool for troubleshooting. Another recent application involved mass transit. We have a customer in Europe who uses our Hall effect transducers to look for ground faults. Trying to detect a ground fault is an application also for a Hall effect transducer, and we also use them in the electroplating industry. And as you know, we make Hall effect sensors or Hall effect transducers up to in the 40,000 amp range, so they're commonly used in the electroplating process industry.
Bill, as we mentioned, we started building Hall probes and Hall effect sensors in 1964, and over the years we built sensors from a few amps to tens of thousands of amps. If we don't have it in the catalog, there's a good chance we've done it in some other project, or we certainly would be interested in developing a sensor for a new application.
All right, well, thanks, John. Appreciate your help today talking about Hall effect sensors and how they're designed and their theory of operation and the advantages and disadvantages of each one. And if you'd like to know more about Hall effect sensors or any other type of voltage or current or power measurement, please go to our website, www.ohiosemitronics.com, or call in, talk to one of our inside technical salespeople at 1-800-537-6732.